please copy down this question, okay, and see if you remember how to do it. Okay, I have two questions that we're going to go over to start off with. They are both exactly like the one you will get on your unit exam on Thursday, okay? They are, I'm not going to say how many steps, that'll spoil it. I'm going to see if you can figure it out. Okay? So yeah, give this one a try. The heating curve is there, okay? Because we said it's important to draw that. That should be like your first step, is drawing the heating curve. So I'll give you a few minutes on that and let's see where we're at. So the first step here is that we have to identify how many steps there are. Okay? Where do we start on the heating curve and where do we end on the heating curve? So if I'm marking my starting and ending points, I start with water at 14 degrees Celsius. So that would be right about here on my heating curve. Right? I'm ending at steam at 135, which is actually like up here somewhere. Okay? So how many steps are there? 3. Okay? There are 3 steps here. The first step is I've got to heat the water from 14 to boiling. Then I've got to evaporate all the water. And then I've got to heat the steam. That's the 3 steps. All right? Anytime I'm heating something up and actually making its temperature change, what formula do I use to calculate the amount of energy? E equals mc delta T. All right, so for step 1, where I'm heating the water from 14 to 100, okay, I'm going to have 385 grams times the specific heat capacity of liquid water, 4.2, times the temperature change, 86 degrees, 100 minus 14. Okay, because it's only liquid water until it gets to 100. Okay, so for that step there, okay, so 385 times 4.2 times 86, okay, is 139.062. Oh, not point, 139,062 joules. Okay, what am I doing in step 2? No temperature change in step 2. Keaton, what formula would I use here?
E equals mLV.
Right. Okay. I'm changing the potential thermal energy or latent heat of the water here by changing its state from liquid to gas. During that time, there's no change in temperature, so this formula doesn't work, but this one does. Right, so I'm going to have 385 grams of water evaporating into steam, and it's going to take 2,260 joules to evaporate every gram. Okay, so I multiply those two numbers together. 385 times 2260, and we get 870,100 joules. That's a lot. Okay. All right, what's going on in step 3? Right, I've got a temperature change going on. I'm heating up the steam, so I'm back to E equals mc delta T. And so that's going to be 385 grams times now the heat capacity of steam, 2.02 joules per gram degree Celsius. And I'm changing it from 100 to 135, so the temperature changes 35 degrees. Okay, so 385 times 2.02 times 35, okay, gives me 27,219 joules. Okay, for that step. Okay, what's my last step?
Just
Add them all together. Yep. All right, so we're looking at 1,036,381.5 joules. Okay. And so that would be 1,036,381.5 joules as our final answer. Okay, how many marks would that be out of? 8. And it's an 8-mark question. 1 mark for drawing the heating curve and identifying your steps. That's your givens for the question. Okay? 2 marks, 2 marks, 2 marks, 1 mark, 8 marks.
What with the 2.02 or something like that? Do we just have to know that, or will it be
It's on the back of your periodic table, and it's also on the test. Like I put it in formulas and stuff like that for the test, but it is also on the back of your formula. Any heat capacities or latent heat numbers that you need are going to be given to you either on your periodic table or in the question. Okay, so now that we've seen one demo, just in case we've forgotten how to do it on Friday, give this one a try. Also, just like the one that will be on your unit exam. Okay, how many steps on this one? 3, yeah, same as the last one. Okay, and this is, I mean, there's only 2 ways I can give you a 3-step problem. You're either going from ice to water or from water to steam. That's the only way I can give you a 3-step problem. Okay, so it's one or the other of these that's on your unit exam. Okay. All right. So if we are looking at this one, we are starting at ice at -15, so that would be about here on the graph, and we're going to water at 85 degrees, which would be about there on the graph. All right, so that is going to be 3 steps. First step is heating the ice to its melting point. The second step is melting the ice, and the third step is heating up the water. Okay, so if we're looking at step 1, because we're changing the temperature of the ice, we are looking at an E equals mc delta T question. Okay, and so that means that we've got 150 grams times 2.116, the specific heat capacity of ice, times a change in temperature of 15 degrees Celsius. All right, so we're looking at 4,761 joules. Okay, and then for step 2, okay, in step 2, we are looking at changing the state of the ice. Which formula do I use here? Michael, which formula do I use here? No, in step 2, I'm not changing the temperature. Okay. It's okay. Okay. Not LV, but LF. Yeah, this time it's freezing and melting, LF, right? So in this case, we're melting, so it's E equals MLF this time. We use LV if we're vaporizing or condensing. We use LF if we're freezing or melting. Okay, so in this case then we have 150 grams times 333 joules per gram. So 49,950 joules. All right, and then in step 4, I've got to heat up the water, changing its temperature, so E equals mc delta T again. Okay, in this case 150 times 4.2 times, we're going to 85, so 85 degrees. Okay, so 53,550. All right, so then my last step is I add all those numbers together. So 108,261 joules. Will be our final energy required. Okay. Everybody all right with those? Okay, so it seems like right now the big thing is which ML formula do I use and when do I use it? Okay, just remember this. The F stands for freezing point. V stands for vaporization point. Those happen at 0. Freezing point happens at 0. Okay, vaporization happens at 100. Right? That's all you have to remember in order to use the right one. Okay. All right, on Friday we left off talking about the first 4 questions. Okay. And did we get through all 4? I don't think we did. Okay. So when you put ice cubes in your drink, okay, obviously it's what's making the drink colder is the second law of thermodynamics. The drink is warm, the ice is cold, energy goes from hot to cold. But eventually, an equilibrium is reached, at least in terms of temperature. Okay? The drink's temperature will drop to around 0, okay? And the ice will still be there. Energy still goes into the ice, because obviously the surroundings then are starting to put energy into the drink. So why does putting ice in there work better than just putting really cold water in? Because in the end, the ice melts and your drink is diluted anyway. Okay, well, it has to do with the heating curve. If I put in ice, ice starts down here. If I put in the coldest liquid water I can, it starts here. Which one can absorb more thermal energy? The ice. Okay? Not only does it have to warm up, which really doesn't take a whole lot of energy, but then it also has to change state. And this state change takes a lot of energy. And that's, for the most part, what keeps your drink cold, is that takes a lot of energy, okay, to melt the ice into liquid water. That's what will keep your drink cold for a longer period of time than just using cold water, okay? Now, is a lot of heat given off when water changes state? So the other way, a lot of energy is obviously needed to melt ice. Is a lot of energy given off when liquid water turns into ice? Well, it has to go somewhere. Okay? If it takes a lot of energy to melt the ice, the energy has to be given back when the water turns back into ice. So yes, a lot of energy is given off in that process. Okay? Back when I was in university, I had a prof who did this demo. He had super cooled water. Okay? Like really, really cold water, well below 0. Okay? He had super cooled it in their special freezer and not disturbed it. It was perfectly distilled water, so it actually didn't crystallize. And he carefully brought it to the classroom, okay, and had it in like this beaker, which had frosted over because it was really cold. And he's like, anyone want to guess what the temperature of this water is? And people are like, it's like 5 degrees, 1 degree, it looks pretty cold. You know, there's frost on the edge of the glass, that's different. It's like minus 20. And everyone was kind of like, that can't be right. Water freezes at 0. And then he just took some salt, just a little like grain of salt, and just went like this. And as soon as the grain of salt hit the liquid water, the beaker shattered and the water froze. And I mean like that. Okay, it froze almost instantly because it was so cold. Okay? It just hadn't changed state. And you can actually do this. I'm going to show you a video. You can do it with bottled water. Right? Put it in the freezer. Don't disturb it. okay? Especially if it's like RO water, or just even like distilled water is even better. It'll drop below 0, but it won't freeze until you do something to disturb it. And that can be as much as make an air bubble travel through it, okay? And then the whole thing will freeze, okay? And when it does, it gives off a lot of energy, okay? Like a lot of steam, okay, stuff like that. Like it just gives off this energy really quickly because it's got to change state fast.
So, show me this here. The water is poured and turned into ice. And
Yep.
Once it went into the boiler, the entire water flows. Like, why does that not happen when lakes when the top layer freezes? And like, if the top layer freezes at all, freezes?
Because there's weight, like there's the pressure of water from above that's enough to keep the stuff below. So you get that layer on top that freezes, right? And that process starts to happen, but there's enough pressure from the weight of that ice that generally it doesn't get much colder than that, right? It freezes and then snow gets deposited on top that insulates and keeps that from, I guess, getting any worse, right? But yeah, it's definitely a pressure thing. Okay, so is that all kind of making sense? How that stuff works? Okay, now if we're back to these questions here, right? When you sweat, and I think we talked about this on Friday, it helps to cool you because as water evaporates, it takes energy away. Okay, and that's why like stepping in front of a fan on a hot day makes you feel cooler. It isn't that the environment is any cooler, okay? The air temperature hasn't changed, the air is now just moving. And when it moves past you, the rate of evaporation increases and you feel cooler because 2,260 joules of energy is being lost for every gram, okay, of water that would evaporate from your body, right? And the same is true if you mist yourself with the hose, if you're at Stampede and they have those like big gates that you can walk through, they're just misting water, okay, on you, helps keep you cool, okay, just because it's got, this thin layer of water that can evaporate. Okay. Now, did we talk about whether like perspiring versus sweating buckets does a more efficient job? Okay, so which is better? Like if you just perspire and get a thin layer of perspiration, or if you sweat buckets? Because obviously some people sweat buckets. It's not better to sweat buckets. You only need a thin layer of water to start evaporating. Okay? If you sweat buckets, you're just like, yeah, you've got lots of water on your skin, but most of it is just dripping off of you. Once it's off of you, it doesn't help cool you. Okay? So, I mean, those people that sweat buckets typically are going to be dehydrated faster, okay, stuff like that. Just perspiring a little bit is actually going to be a bit better in terms of not getting dehydrated. In terms of who gets cooler, it's about the same. Okay? One person just uses more water to do it. Okay? And I mean, some people are just like that, right? Some people, they can be running stairs like crazy and they just go like this and they're good. Okay? Whereas other people are, they walk up one flight of stairs and they got to change their shirt. Okay? Because, they got the sweat line down the back already. Okay? The Oilers way back, before Connor McDavid, had a goaltender named Nikolai Habibulin. And this guy sweat buckets. Okay? Like he would lose 10 pounds in a game, and it was all water. He would literally sweat out 10 pounds worth of water in a game. He would come, whenever there was a stoppage in play, he'd come to the bench and he'd get a new blocker and a new catcher because they'd be soaked. Okay? They actually caught on the crease cam, that little camera that they have at the bottom of the goal, they actually caught once. He had holes drilled in his skates to drain the sweat. Otherwise he would have sweat in his skates. So he had little holes drilled in the bottom, and the crease cam actually caught water dripping, sweat dripping out of the bottom of his skates. Okay? That's why the Oilers were no good in a shootout for the longest time. Because by the time they got to overtime in a shootout, this guy was like 12 pounds lighter. He was cramping up, totally dehydrated, okay, and it wasn't any good. All they had to do was, anybody was beating Oilers back then, but they got into a shootout, it was almost a guaranteed win if Habibulin was in goal, because he just didn't have the endurance, because he'd be so dehydrated by that time. I mean, he'd come, get his new blocker, his new mitt, and 2 new water bottles, and the guy was like drinking like crazy. So it doesn't do any better to sweat buckets. You just sweat more. There's nothing good or bad about that. It's just you drink more, you sweat.
Is it just a genetic thing?
Yeah, genetic things. The way some people's bodies are designed, their sweat glands are more active or more productive than other people who just perspire a little. There's also male and female difference as well. Men tend to sweat more for whatever reason than women do, but it's just, yeah. Some people sweat buckets. I played basketball with a guy who, he wouldn't wear his uniform during the warm-up. Because he would have to wring it out after the warm-up. He was just, yeah, you couldn't set a screen on the guy, you could just slide off, he was like slimy, slippery, right? Yeah, I wouldn't want to play defense on the guy, cause you just be like, oh, gross every time you touch him. Okay, but just some people are like that. Okay, we talked about number 4 kind of already when we talked about the ice cube thing. You definitely want to put ice in a cooler rather than cold water, because the ice has to change state, which means it has greater ability to absorb energy than does its liquid counterpart, which is already changed state and is at 0 degrees Celsius. Okay, and what about this one here with the gardeners spraying their crops? So right before a frost, if it's going to be just a mild frost, if, like people who have orchards, like apples or even tomatoes to an extent, golf courses will sometimes like water the green right before it's going to freeze. Okay, what's the purpose of that? It's going to freeze. What's the purpose of putting more water on it to freeze? When water freezes, it. What were you
I
going to
was
say?
gonna say like if you spray the grass with a lot of water, then like the water on top will freeze with the grass.
Exactly. If you get a thin layer of water on the fruit, the grass, whatever, when the water freezes, it releases energy. That energy goes into the grass or the fruit or the leaves or whatever and actually protects them from freezing. If it's just cold air around, then the plant is going to freeze. Does that sort of make sense? This only works if it's a mild freeze. If it's going to get to -10, the ice, the water's going to freeze, so is the fruit. Okay, but if it's just a mild freeze, -4, something like that, okay, it can work. All right, I would like you guys to try. Well, we'll take a 5-minute break. Then I'm going to want you to try 6 and 7. Okay, so we'll take a 5-minute break, then we'll try 6 and 7. Okay, so let's get to work on 6 and 7. Okay, here.
Thank you.
This is water at 100, right? Right there is water at 100. This is steam at 100. That's one step. What happens during this step? It changes state from liquid to gas, which requires that much energy, or much that comes up to.
Oh, I was thinking of the wrong
That's okay. I know you're thinking MC delta T, like it's 0. I'm like, you're totally right. This is the wrong formula.